All right, we're going to talk about section 6.4 in the book today, and we've actually seen the thing we're going to talk about today before. I talked about it on November 8th. I'll link that YouTube video as well. They call this the second fundamental theorem of calculus. I'm just going to call it fundamental theorem of calculus part 2. All right. And okay, so as a refresher, what should you think of when you think of the fundamental theorem of calculus? All right, well, if you have some function, little f, that's not too bad. And what I mean, I'll actually write it out for once. That's, okay, it has to be bounded. And for our class, we'll use piecewise continuous. Continuous on A to B. All right, and now, all of this, I haven't written out before. I used to always jokingly say just the phrase, not too bad. Okay. You don't want your function to blow up to infinity. You don't want your function to just be radically discontinuous. So you can have kinks and stuff, that's fine. We have piecewise continuous. We could even have some jumps and stuff, that's fine. We just don't want to like blow up to infinity. We don't want to be too discontinuous and just nasty. So, all right, in the past, I just always said not too bad. But if you have a little f defined like this, then, well, the integral from a to b of little f of x dx is big F at b minus big F at a. I'll say provided big F prime is little f. Okay, so this is what I'm going to call part 1, but we're here to talk about part 2. And part 2 says if you define a function, let me give myself a little bit more room. All right, previously I used A for area, but to use the same notation as the textbook, no, you know what, I like A. If you define an area function to be an integral from some fixed value up to x of a function, t, and again, this little f function should not be too bad. It should be bounded, meaning it doesn't blow up. It should be piecewise continuous, meaning on chunks it still looks pretty good. Okay, so if you define an area like that, then the derivative of the area is little f. And written out in a better way, the derivative of an integral from a fixed value up to, right, the variable that I'm taking the derivative of is sliding out and telling me how much area to take. And now I have f of t dt. I will get f of x. So I'm taking the derivative of this area function, and what gets spit out is the height, and then it's at the point of interest. Okay, that's the fundamental theorem of calculus part 2. That's it. I actually already talked about this, but how can we make this harder? So, well, we'll get harder in a bit. Let's just see why this matters, or how it might come up, or even just this idea of defining a function based on an integral. Okay, it happens in engineering, it happens in statistics, it happens in a lot of mathematics. And so, okay, let's talk about stats for a moment. So in stats, there's this thing called a z-score. And essentially it measures how far away you are from the mean of something. So if the average height for a guy in the US is 5'10", and I'm 5'10", then my z-score would be 0. But if the average height is 5'10", and I'm 6 foot, that's 2 inches higher, my z-score, well, if the standard deviation is 2 inches, it might be 1, but it's going to be a positive z-score because I'm a little bit bigger. And if I was 5'8", it'd be a negative z-score because I'm a little bit lower. But z-scores essentially measure how far you are from the mean. And the way, okay, I should know better. You never want to draw the axes before you draw your function. It's just easier to draw a hump and not worry about where the peak is and then draw your axes afterward. Okay, anyway, so here's z equals 0. And just to continue with heights for a little bit, let's say z equals 0 corresponds to a height of 5'10". Should be a little double mark. So maybe, here's z equals 1. And okay, this area here is the probability that some guy is, and we'll just say this corresponds to 6 foot. Okay, probability some guy is between 5'10", and here's his height, and 6 foot. So the probability that a person, and this is for a guy, it'd be a different curve for females, and it essentially just shifts this down like 4 inches. But what it is the integral from 5'10" up to 6 of some probability distribution. And it turns out that what goes in there is e to the negative, and then I'll just simplify it a little bit, x squared dx. Okay, it's actually something like e to the negative, and then x minus the average over sigma. We're going to square this, and then we have like 1 over sigma root 2 pi, and maybe there's like a 1/2 here. It's actually a lot grosser, but at the end of the day, it has the shape of e to the negative x squared. So we'll just focus on that. So a probability is defined via an integral, and we can get this running probability or a cumulative probability where we just continue out this way. And so we're interested going from 0 out to some, okay, so then there's some x and there's some z. The probability of being in this entire window here, that's going to be the integral from 0 to z of, and then we have e to the minus x squared dx. And if I took the derivative, and I have to do it with respect to what I'm moving around. So I'm moving around my z-score. So I take d dz, and of this integral here, e to the minus x squared dx, and I'll get e to the minus z squared. And you can kind of think of this like a probability that someone has a certain height, but not quite true. This is called a probability density function when you take the derivative of the cumulative. Okay, I'm getting too much on a tangent, but the point is, in statistics, we define stuff, the stuff is probability, based on integrals. In engineering, especially electrical, you do a lot of integral type operations, and your book talks about this, what's called the psi function. So psi of x is defined as, this is a definition here, integral from 0 to x of the sinc function, which is sine of t over t, dt. And again, there is no closed form expression for this. And what I mean by closed form is I can't just write out a function for it. I have to write this down using the integral. So the book has a table of different values. It has x and psi x, and like at 0, it's 0, because if x is 0 up here, then there's no area, because the width is 0. And at 1, it's like 0.9 something, I don't know. It doesn't matter. Okay, so the idea of defining a function based on an integral happens. Let's look at the derivative of psi of x. All right, well, this says take the derivative of the integral from 0 to x of sine t over t dt, which, fundamental calculus, it's sine x over x. Okay, and I could make your life even harder and use the chain rule. I could say, let's take the derivative of psi of x squared. Okay, just don't panic. I have an outside function, so I take its derivative. It's sine blah over blah, and I leave the inside the same, x squared, times, and then I take the derivative of the inside, 2x. Okay. And I could write this exact question, derivative of psi of x squared, as an integral from 0 to x squared of sine of t over t dt. And in this form, it might look scary and weird. But in this other form, maybe it looks much more like the familiar chain rule. So let's kind of bridge these two. And I want you to have all this in mind as a motivating example on how to arrange stuff. But in general, sorry, just in case it's not clear, the answer to this guy it's the same. I just rewrote it. Right? But okay, let's look at a slightly more general part 2 fundamental theorem of calculus, which says if you want to take the derivative and you start at a fixed value and you go up to a function of x, so now I have g of x as a limit, very similar to what I just erased where I went up to x squared, and then I have a different function on the inside. Well, just like before, you sort of take the derivative of the outside, and the outside is a little bit weird, but it's this integral operator. And so I'm taking the derivative and I get into just f, but I leave the inside the same. And again, inside is sort of a bad word for it now, but the quote unquote inside is this upper limit. So it's f of g of x times, and then g prime of x. I have a chain rule. So this is sort of like the more general FTC part 2. Okay. And so we see it happening here. I just didn't write down with an integral operator because if I write it down this way, it looks more familiar. Okay, okay, let's do a few questions from the back of the book. So something that I thought was kind of good. So all of exercises 4 through 6, they all have the same kind of format. They say write an expression for a function f of x, so that's our goal, with the given properties. And so we'll just say find express. There we go. Express f of x where, so I'll look at 4. F prime of x is sine of x squared, and f of 0 is 7. Okay, well, if I want sine of x squared to be my derivative, then to build a function that has that, I put my desired derivative on the inside of an integral, and I have to change the variable to a dummy variable, but then the one that I want, the variable of interest, is what goes up here as the top. Okay, now my bottom limit has to be a fixed number, and the number that I use, I look over here for motivation. Okay, so when I plug in 0, I need to get 7. Okay, well, off the top of my head, I don't know much about how this integral behaves. But if I want to make my life easy, right, if I just put a 0 here, and at first I say, well, maybe this is f of x. I'll do equals with a question mark. Well, now then f of 0 would be the integral from 0 to 0. Aha, that's 0, which is not 7. I wanted to get 7. So what I do is I say plus 7. Okay, so now this function, I have now expressed the correct answer, f of x. Let me convince you it's the correct answer. So is it true that if I take the derivative, I get sine of x squared? Well, yeah, if I take the derivative, then the 7 is going to die. And here I use the fundamental theorem of calculus. And yeah, I get sine of x squared. All right, is it also true that if I plug in 0, I get 7? Well, yes, because if I plug in 0, then I have the same limit on top and bottom. That means there's no area because there's no width. So the integral dies, and I'm left with 7. All right. The one in the text that has a solution, if you click on it, let's go up, is number 5. So I would encourage you to take a look and see if you can figure it out. But it says f prime of x is the sinc function, which is sine x over x. And it says f of 1 is equal to 5. Okay, so give it a shot. They have the answer in the text, and it should be very similar to what I did. All right, I think you should all look at exercises 7 through 10, and that you should glance at them and think, yes, I can absolutely do this, all right? And in case you can't, I guess I'll do one. So let's see. Both 7 and 9 have solutions given. So I guess I'll do 10, for example. And it gives you a little curve. Oh, let's redo that bottom. All right. And the curve looks something like this. Okay. And this is little f of x, or little f of t. Sure. Let's do that. And it says define big F of x as the integral from 0 to x of little f of t dt. Right, so I get a slide around x, and then this is the area of interest. And it says graph big F of x. Okay, so obviously I can't really graph it with much accuracy. They don't even give any numbers. They just draw a picture like this. So there's no tick marks or anything. So what they really want is for us to capture the shape of what f might look like, big F might look like, right? So one thing that I know is true is that at 0, big F, so I'm now graphing big F versus x. At 0, if I slide this x value all the way over to 0, there's no area. Okay, now as I start to move to the right, my area is increasing, but it's sort of increasing slower and slower. The amount of area I get in this first, right, once I get to this first tick mark versus this next tick mark, I have more area here compared to here, which means I gained more in my first unit compared to my second unit. But I'm still gaining. And then I can go to my next unit over. I'm still gaining, but again, this blue area is less than the red, which is less than the black. And those are telling me how much f is growing. So, okay, I need to grow, but I need to grow less and less until, let's see, until I get to about here. Curvy line. All right, so what does that mean? Let's see, I grow, but I grow slower and slower and slower, and I get here, but, ooh, okay, so I just made a mistake. So let's talk about my mistake. This is the first pass. It's not quite a mistake, but whatever. I was flattening out, right? I was flattening out because I want to grow less and less. But I shouldn't flatten out completely to where my slope is 0 because I'm still gaining area here. There's still, okay, really, just remember, f prime is little f. So I should have my derivative be approximately the height of little f. Again, they don't give any numbers, but you know, this height here, well, it's a little less than a half of how I started. So what I should do, if I really want to make this accurate, all right, let's redo it, is when I get to this dotted line, this x value where I have the slowest growth, let me give myself a tick mark for reference, some kind of positive, okay, maybe it has that kind of slope. Well, then the slope that I begin with should be at least twice that. So I can kind of bang, right? Okay, this is better. Not a big deal. And now, then I want to go, and I continue to increase, and when I get here, I need to have the steepest I've ever had. So now I kind of have like a, you know, bang. Just, I want this guy to be even steeper than this guy. And then I can start to mellow out, and by the time I get here, well, now I have a derivative of 0. So now I come up, and then I level out again. So sorry to make it so messy. Let me sweep it out in green. That could be an example antiderivative curve for the derivative of the camel hump up above. All right, so we should be able to picture things like that. Then all of questions, this is 11 through 16, they all have the same flavor, which is take a derivative of an integral of some kind. All right, so for example, no, they give an answer to that one. I'll do 12 here. They have integral from 4 to t of sine. Oh, so then I need to change 1 second. This is d dt. Okay, so now they have sine of root x dx. All right, well, the bottom is fixed. Check. And now I'm good to go. I have up here is just a single variable. It's not a function of it. I mean, it is just a very simple function. But okay, so what do? I have sine of root t. Boom, done, all done. Problem 16 on this list, problem 16, is one that we looked at before. It's the derivative of psi of x squared. Okay. I think you can do all of the problems on that list, so that shall be fine. We have intervals where that could be interesting. Yeah, I would encourage you to think about problem 17. You might want to use Wolfram to graph, but it's the bell curve. So they care about this function here. And they want to know when, so this function, we'll call it big F of x, when is that concave up and when is that concave down? So think about that, give it a shot. I think that's pretty much, if you can do that, then I think I have faith. Let me just scan these real quick. Find F prime, decreasing. Okay. So once we get to 34 through 37, we finally have a different flavor of problems. And I think, if you can get this far, you might be good for the chapter. And if you want to go beyond and ask questions, that's great. But, in fact, I could even just, even after 37, they continue the same flavor. So 34 through 41, they're all similar. Okay, and they all use the chain rule. So let's do one of those. They use chain rule integrals. Okay, great, I love it. So we'll start easy. We'll do 34, and then I'll also do 36, or maybe even, I'll do 36. And I would encourage you to look at 35 and 37. And then that's where I'll stop for today. So 34, it says, what's the derivative of the integral from 0 to x squared of the natural log of 1 plus t squared dt? Okay, so it's a chain rule, and this top limit is what I want to think of as like my inside function, and my outside function I think of as the stuff on the inside the integrand. So what I get, I have, well, okay, actually my outside function, I'm sorry, I misspoke. My outside function is if this was just an x. I'll do this in two ways. So the first way is very just mechanical. It's following the steps that I laid out up here. Okay? So what does the step say? It says takes the function on the inside, plug in the upper limit, then take the derivative of the upper limit. Okay, so let's do that. Super simple. Natural log. And now instead of t, I plug in my upper limit. So I have x squared times, and then I do the derivative of my upper limit, 2x. Okay. All right, well, where, this is it. This is the answer. But if that just feels very mysterious, just think of having a function defined as the integral from 0 to x of natural log 1 plus, not x, go back, 1 plus t squared dt. Then a prime is natural log of 1 plus x squared. That's it. That's all it is. Right? That's the fundamental calculus. And so if this is the case, then a of x squared would be the integral from 0 to x squared of the natural log 1 plus t squared dt. And we know that if you take the derivative of a of x squared, what you should get is a prime of x squared times 2x. That's a prime of x squared times 2x. That's the chain rule. And now we have a prime. And hey, what is a prime of x squared? Right? Well, now that's x squared, so I have to replace an x with an x squared. So I have the natural log of 1 plus x to the 4th. Okay, that's squared. Right? So now I can just plug this in, and you get the same answer that I said. Okay, but this shows you how it is the chain rule. Let's do one more like this. Right, and yep, okay. So 36, and the reason that I want to show you 36 is to show you an idea of, well, you'll see. So here my bottom limit is a function, my upper limit is a constant, and then I have sine root t. No, I don't. Sine root x dx. Okay. So we have two choices. Well, I guess we really have one choice. What we need to do is manipulate this inside to get it to match the format we're used to if we want to just use this formula here, okay? Because the formula, as written, is for when your constant is on bottom and your function is on top, all right? So how do we make it match? We use rules of integrals. This is equal to the derivative of, oh my gosh, of, and if I put a negative in front, I can flip the limits. Okay, now I'm ready to use the chain rule in the fundamental theorem calculus. I have my negative comes along for the ride. Oh, don't be lazy, Anthony, just write out the inside. I have sine root x dx. Okay, so my negative comes along for the ride. Derivative, so let's see, I do derivative the outside, leave the inside the same. So that's sine root, and then leave the inside the same, 2t. Times, now derivative of the inside is 2. Okay, here's my answer, which I could make prettier as negative 2 sine of root 2t. Right, but this idea of manipulating to get to the form you want, that's what they use in 37. So let me give you a hint for 37. 37 says take the derivative of the integral from negative x squared to positive x squared of e to the t squared dt. Great. So here's your hint, and then I'm going to stop and call it a day. You want to think of this as the derivative of, and then I'm going to end up adding two functions. My first function is the thing that integrates from negative x squared to 0 of e to the t squared dt. Plus, and my second function integrates from 0 to x squared of e squared dt. Right? So there's your hint. Break up the integral, hit the first, hit the second. You might need to flip things. All right, that's it for today.